To finish up with confidence intervals, we're going to finish up the same way that we did with proportions. We're going to finish it up with means. And we're going to solve for a sample size, but we're going to remember a few things first. So the first thing we're going to remember is the formula for constructing a confidence interval for means for one sample. We take our point estimate of x bar, which is in the middle of the interval, and we add and subtract the t star critical value, which is multiplied by the standard error, which is s sub x over the square root of the sample size. So that's the formula for constructing a confidence interval for one mean. Now, if I multiply together the t star and the standard error, if I multiply those two values together, then what do I get? I get the margin of error, which is ME. So margin of error is when those two things are actually multiplied together. That is the distance from the middle of your interval out to either side. There are three conditions that we check when we construct a confidence intervals. There are three conditions that we check when we construct a confidence interval. What are they? Random, 10%, and normal. Now, why do we check them? So the first one that we check is random, and that has to do with the x bar. The reason, and this was on your workout that you turned in, why do we check the random condition? Yes, it ensures x bar is an unbiased estimator of mu. That was perfect. Couldn't have said it any better myself. Now, the next condition that we usually check is the 10% condition. Now, just so you know, that is based on the standard error part of the formula. So it's kind of out of order, but it's fine. 10%. Why do we check the 10% condition?
Ensures we have a normal, ensures we have independent observations and good variability from population.
Yeah, the 10% condition, we check it to ensure that we have independent observations and good variability from the population. Yeah, that's perfect. Couldn't have said it better myself. Ensures we have independent observations and good variability for the population. Standard deviation, we've got good variability. We've got a good sample size, or not sample size. We've got a good representation from the population. And then the third condition that we check is the normal condition, and that has to do with the t star critical value. Now, why do we need to check normal for t star? This ensures, perfect. This ensures we have a normal distribution and can use t. Because remember, t is a normal distribution. It's not the standard normal distribution, but it is a normal distribution. There's lots of different normal distributions in the world, but it is a normal distribution, and we need to make sure that we can use it by making sure that we have the normal condition met. So those are our conditions, and those are why we check our conditions. Those are the same three conditions that we check for proportions. Same reasons. It's just a different formula. Cool? Cool. All right. Why or when do we use t and when do we use z? How do we know when to use the t distribution and how do we know when to use the z distribution?
T is for means, Z is for proportions.
T is for means. Z is for proportions. Easy enough. And what is the difference between a T and a Z distribution?
Z is set and T is like variability.
Good. Z is a standard set distribution that never changes. T is based on sample size and has more variability in it. Z distribution is standardized. Standardized. There we go. And does not change. T distribution changes as N changes and has more variability. Especially in the tails. So we've got more variability, especially in our tails for the T distribution. Z distribution is standardized and doesn't ever change. It's always going to be set and the same. All right, cool. So that was just some recapping, making sure to remember all that. Any questions about any of that? Cool. Now we're going to look at how did we solve for a sample size back when we were doing proportions. So when we were doing proportions, we had our desired margin of error had to be greater than or equal to the Z star critical value times the square root of p hat, 1 minus p hat divided by the sample size. And we had to solve for n. Now, does this ring bells?
Yeah.
We had to solve for n. We had to divide by the Z star critical value. We had to square both sides. We had to do some cross multiplying, blah, 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 blah. You guys loved it so much. Most of the time we didn't have p hat because we hadn't taken the sample yet. So what did we use for p hat? 0.5. If we didn't know what p hat was, we would use 0.5. Sometimes we would use a previous p hat from a previous study. And that was how we solved for the desired margin of error. So it would seem like to do this for means, we would use the desired margin of error, and then we would use the margin of error part of the formula, right?
Sure.
All right. That would seem logical, but there's a problem. We need the T star critical value in order to solve for this margin of error here, right? Does anyone remember how to get the T star critical value? You use your calculator. Where do you go to inverse T? Think about what you have to put into inverse T. You need the area. You need the degrees of freedom. And how do you get degrees of freedom? N minus 1. If I'm trying to solve for what sample size to take, I don't know N. I'm literally trying to solve for it. So how am I supposed to get a T star critical value when I haven't taken a sample yet? You can't. So what do?
Different formula.
We just don't do it, right? No, I'm kidding. Remember, your Z star critical values are kind of your upper limits, right? Remember, we'll never get a T star that's any big or any smaller, or so it's your lower limit. Your Z star critical value, once you get to about 100 for your sample size, they start to look very similar anyway. So for this situation only, we will use Z star to estimate the T star, okay? So it is going to be desired margin of error has to be greater than or equal to the Z star times the standard deviation of the sample over the square root of N. It's supposed to be T, but remember, that's what we just talked about, because I can't get a T star because I don't know the sample size. So again, we're going to make a little note here. We are only using Z star because we cannot get T star without degrees of freedom, which uses n, which is literally what we're about to solve for, is n. So like, I'm kind of stuck there. I can't get a T star without n, but I'm trying to solve for what sample size to go take. So I have to use something. So I'm just using Z star in this one situation for means, only because I have to estimate it with something. There's also another problem with this formula. Kind of the same problem that we had over there with p hat. If I have not taken the sample, I'm trying to figure out how big of a sample to go take, then what's my sample standard deviation? I don't have one yet. So I'm going to have to estimate S sub x with a previous standard deviation, kind of like I did with p hat. There is no like guess value because means can be any number, so that it would have to be given to you in the problem. Okay, so we're going to estimate S sub x with a previous studies standard deviation. And that, again, will be given to you in the problem. Okay? Okay. Y'all ready to do a problem? Ready to do some algebra? Y'all love algebra, don't you?
So much.
Sure. Let's go with that, Miss Lakey. Whatever you say. Yeah, we have a complicated relationship with algebra.
Okay.
All right, Mr. Sines wants to estimate how much time a Kenny Boyd High School student spend on homework on average during a typical week. He wants to estimate mu at a 90% confidence level with a margin of error of at most 30 minutes. A pilot study indicated that the standard deviation of time spent on homework per week was about 154 minutes. How many students need to be surveyed to estimate the mean number of minutes spent on homework per week with 90% confidence and a margin of error of at most 30 minutes? All right, so we want our desired margin of error to be greater than or equal to, again, I'm going to use Z star only because I have to, and then standard deviation over the square root of the sample size. Yes?
How do you know when you're supposed to use Z star in this situation?
So if anytime you are solving for a sample size, you have to use Z star. And that's the only time you're going to use Z star in it for means. And I'll be honest with you guys, there are times where I kind of like space out and I forget and I try to use T star, but as soon as you get to inverse T and you try to put in degrees of freedom, you're like, oh duh, I can't use that. Okay. You kind of get stuck pretty quick. It's not like you're going to go through and do anything before you realize you should use Z star. Okay. All right, what is the desired margin of error? 30 minutes. Okay. Oh boy. The Z star critical value for 90%. Does anyone happen to remember it?
1.6.
Look at you guys. 1.645. Nice. What is it for 95%? 1.96. You got it. Cool. All right. Standard deviation from a previous study or pilot study? 154 over the square root of the sample size, which is what we're going to solve for. All right. The algebra steps are slightly different than they were with the proportions because the square root is only on the bottom of the fraction, not the whole fraction. So this is going to be slightly different, but let's go. What's the first step? We're going to divide both sides by 1.645. That's our first step. $18.237 is greater than or equal to 154 over the square root of the sample size. Again, at this point, you should not square both sides because the square root is only on the bottom of the fraction, not the whole fraction. So what should we do though?
Multiply by 1 square root of n.
Yeah, we're going to multiply both sides by the square root of n. We're going to multiply both sides by the square root of n. Okay? I'm going to move up here now. Whee! So I've got 18.237 times the square root of n is greater than or equal to 154. Okay, what now? Should I square both sides?
Yes.
Not yet. The square root sign is not by itself yet. So I need to divide by the 18.237. So now we have the square root of n is greater than or equal to 154 divided by 18.237.
8.44.
8.44. And now what should we do? Now we square both sides. So the squaring both sides happens at the very end with means. Now we square both sides. And our sample size needs to be greater than or equal to 71.234. So Mr. Science says, AP Stats class, how many students should I talk to?
72 people.
At least 72. Remember, because this says n has to be greater than or equal to this, we always have to go up here. So we need to talk to at least 72 students. Cool. What questions do you guys have about this? Easy enough. Let's do it again. Sort of. All right. You're like, oh, dang. What does that mean? All right. High school students who take the SAT math exam a second time generally score higher than on their first try. Past data suggests that the score increase has a standard deviation of about 50 points. How large a sample of high school students would be needed to estimate the mean change in SAT score to within 2 points with 98% confidence? Oh, man. I threw you a curveball, didn't I? Anybody know what the curveball is? Let's just start the problem and you'll see it. Desired margin of error has to be greater than or equal to. Again, we're using Z star because I can't use T star because I don't know degrees of freedom because I haven't gotten a sample size yet. S sub x over the square root of the sample size. No, that's right. So what is the desired margin of error that I want to be within? We do. 2. Has to be greater than or equal to. What's the Z star critical value for 98%? Ah, there's your curveball. I gave you a problem that you don't know the Z star critical value for already. Do you remember how to find it? I'll give you a hint. So if I have 98% in the middle, I have 1% on either side. That means I have an area of 0.01. And instead of using inverse T, I go back to using inverse norm because it's a normal distribution. This will get you your Z star critical value for 98%. It's almost like Miss Lakey wanted to review that with us. Weird. Crazy. Strange. It is 2.34. All right, what's the standard deviation? 50 over the square root of the sample size. All right, at this point, it's your turn. Solve for n. You got this. I will tell you, because some people freak out, it is a very large number. It's a very large sample size. So you all find it, and we will reconvene momentarily. Whoops. All right, so we did what first? We divided 2.34 on both sides. And we got 0.855 is greater than or equal to 50 over the square root of n. You guys want to know a cool math trick? Watch this. What would be the very next step? I would multiply by the square root of n. And what would be the very next step? Divide by this guy, which would move it over here. So really, what am I doing? I'm really just switching these guys. Okay? So you can save yourself a little bit of writing if you just recognize that all you're doing here is multiplying and then dividing, and you're just switching them. You're kind of cross-multiplying-ish. Yep, that's a thing. So you can kind of save yourself a little bit of writing if you want to, and you can just say the square root of n is greater than or equal to 50 over 0.855. Again, just switching those two things is all you're doing. That just saves you a step. And then right here, all you're doing is squaring both of these sides. So you can kind of write 3 steps in one right there. And then you have your answer, n is greater than or equal to. Now, I'm going to tell you guys that based on what I saw on your paper, you all have slightly different answers. Why?
Because you rounded.
Yeah, some of you guys rounded a little bit shorter than others, which is fine. So I will tell you it is somewhere around 3380-ish. Okay, so if you're anywhere in the 3300s, you're fine. Okay, if you're not in the 3300s, something happened with your algebra. Yes. All right, questions about any of that?